In this video, I'll be discussing how you can assign oxidation numbers for organic molecules because the process is going to be slightly different from what we looked at before. So for organic molecules, there's some weird things going on that we have to account for, namely the fact that we introduce a new rule with hydrogen. With organic molecules, we get a lot of carbon-hydrogen bonds. And for hydrogen, when hydrogen is bonded to carbon, its oxidation number is going to equal 0. So we said before that hydrogen is normally +1. Well, when it's bonded to carbon, it's going to equal 0. And we'll see why that is in just a second. But that's a new rule that we're going to add to our sort of rule book here. And that's going to be, like I said, very important because organic molecules have a lot of those kind of bonds. And also for organic molecules, if you have multiple carbons in your molecule, it's very likely that the carbons will all have different oxidation numbers depending on what's going on with them. So we need to account for that too. So that's why we're going to introduce a new equation to help us solve for the oxidation number of these organic molecules. Technically, you could use this equation for the other molecules too. It's just that the algebraic way is usually easier. But in this case, we're kind of stuck using this one for the carbon-based molecules. So the oxidation number is going to equal the number of valence electrons your atom has minus the number of electrons that are split for that atom. And we'll get into that in just a second when I show you. But basically, number of split electrons is based on electronegativity. If your atom is bonded to a very electronegative atom, the electronegative atom is going to get all the electrons in that bond. If there's no electronegative difference between your atoms, then the electrons are split equally between the two. And I'll show you what I mean by that when we actually look at a structure. So let's go ahead and look at an organic molecule and see what I mean by this new approach that we need to take with calculating the oxidation numbers. So let's look at this ethanol molecule and start making sense of this new equation that we've introduced. So based on our new rule for hydrogen, all of these hydrogens that are bonded to the two carbons, all the ones I've just circled in yellow, are going to have oxidation numbers of 0. And if we wanted to apply our equation to that, let's go ahead and do that. So each of these hydrogens is going to have one valence electron minus number of split electrons. Well, carbon and hydrogen don't have an electronegative difference. Therefore, they're going to split each of these single bonds evenly between them. So remember, there's 2 electrons in a single bond, and if you're splitting that single bond evenly, that means each atom gets 1 electron. So that's -1, and that's going to give us 0 for our oxidation number. Now for this hydrogen down here that I've circled in orange, it's bonded to oxygen. Therefore, it's going to have a +1 oxidation number. The rule here applies because it's not bonded to carbon. So it obeys the rule, and it's going to be +1. Oxygen is also going to obey its rule, which is oxidation number being -2. But let's apply our equation and see why it's -2. So oxygen has 6 valence electrons, and we're going to subtract. I'm going to do parentheses here because we're going to have to add up a few things. So the first thing you want to take into account is lone electrons. So we've got 1, 2, 3, 4 lone electrons on that oxygen, so we're going to put that first. And then we got to look at the 2 bonds that this oxygen has. It has a bond going to hydrogen, and it has a bond going to carbon. Well, we know oxygen is part of Funkelbrice. It's very electronegative. And that means oxygen is going to hog all the electrons to itself. So oxygen is not going to split the electrons in these bonds equally between hydrogen and carbon. It's going to hog them all to itself because it's so electronegative. So we're going to give oxygen both the electrons in this bond and both the electrons in that bond. So that's -2 and -2. Because we're giving both the electrons in both of those bonds. So subtract all of that out. 6 minus 4 is 2. Minus 2, that's 0. And then minus 2 again, that's going to be negative 2. So we kind of take it for granted that oxygen is usually negative 2. But there's actually a reason why it's negative 2, and it's because of this equation up here about the electron splitting. So that's why oxygen is normally negative 2 for its oxidation number. But the real question here is, what are the oxidation numbers on these two carbons? We've got all the rest of them. All these hydrogens are 0. This hydrogen is plus 1. The oxygen is minus 2. But what about the carbons? Let's use our equation here to help us out with getting the oxidation number on those carbons. So I'm going to look at this green carbon first. So for the green carbon, carbon has 4 valence electrons, and then minus, so it's bonded to 4 different things because we have 4 single bonds. So we've got a bond going to carbon, and we've got 3 bonds going to 3 different hydrogens. Well, carbon to carbon is just carbon bonded to another carbon. There's no electronegative difference there. So this bond right here is going to get split evenly between those 2 carbons. So each one is going to get 1 electron, so that's 1 minus 1 here, because carbon and hydrogen are going to split it equally, minus 1 up here, and minus 1 for that hydrogen. So each of the hydrogens takes off 1, and the carbon takes off 1. So that's 4 minus, add all these up, that's 4 minus 4. And we get 0. So the oxidation number for that green arrowed carbon is going to be 0. Well, what about the blue arrow carbon right here? So again, carbon has 4 valence, so that's what we start with. Minus, let's see, we've got a bond going to a hydrogen up here, we have a bond going to hydrogen down here, and we have a bond going to this carbon over here. So there's 1 electron from that hydrogen, there's 1 electron from that hydrogen, and there's 1 electron from that carbon. So that's minus 1, minus 1, minus 1. But what about the oxygen? Well, remember, even though there's a single bond going to the oxygen, oxygen is very electronegative. And we said that oxygen is going to steal all those electrons from that bond. So carbon's not going to get any effects from that bond as far as electrons go. So we'll say 0. Because oxygen is going to get both of those electrons to itself. So 4 minus 1, minus 1, minus 1, minus 0. That's basically 4 minus 3. That's going to give you plus 1. So the oxidation number on this blue arrow carbon is going to be plus 1. And that's how you use this equation up here for these organic molecules. You have to take into account, are your bonds going to electronegative atoms, or are they going to atoms that are where there's no electronegative difference? Electronegative elements get all the electrons. If there's no electronegative difference, then you just split the electrons equally. And that's how you calculate the oxidation number for these organic molecules. You could also use this equation on the non-organic molecules, like I said before, but typically the algebraic method is going to be easier for the non-organic molecules. But for organic molecules, we're kind of stuck using this because we have to.